Welcome, dear friend. I've been quietly awaiting your arrival. Here, within the ancient stillness of Sleepy University, you may find true solace. I am Chancellor Eldrin, here to gently guide your way. Now, I activate my balm of stars, a soft light to comfort your rest and ease your learning. Come, let us softly explore the vast wisdom that waits, where quiet calm brings clear understanding. For millennia, humanity has looked to the stars, driven by an innate curiosity about what lies beyond our world. This isn't merely a scientific endeavor, it's deeply woven into the fabric of our being, a yearning to understand our place in the cosmos. But the drive to explore Mars isn't simply about satisfying that ancient curiosity. It's about something far more pragmatic, the long-term survival and evolution of our species. Earth, for all its beauty and bounty, is a finite system. It's subject to a multitude of threats, from asteroid impacts and supervolcanic eruptions to the slower but equally concerning effects of climate change and resource depletion. To place all our eggs in one basket, so to speak, is a risk we cannot afford to take. Mars, while undeniably challenging, represents a potential Plan B for humanity, a place where we can establish a self-sustaining civilization and ensure our survival even in the face of catastrophic events on Earth. But it's more than just insurance, it's about growth. Expanding beyond Earth will necessitate innovation in countless fields, from closed-loop life support systems and advanced robotics to new materials and energy sources. These innovations will not only enable us to thrive on Mars, but will also have profound benefits here on Earth, helping us to address some of the most pressing challenges facing our planet. Consider the concept of planetary boundaries. These are the limits within which humanity can safely operate without destabilizing the Earth's systems. We are currently exceeding several of these boundaries, pushing our planet towards a potentially irreversible tipping point. Establishing a self-sustaining colony on Mars forces us to confront these limits head-on. We must develop closed-loop systems that recycle resources, minimize waste, and operate within a finite budget of energy and materials. These are not just technological challenges, they are fundamentally philosophical ones. They require us to rethink our relationship with the environment and to adopt a more sustainable way of life. The lessons we learn on Mars will be invaluable in helping us to create a more sustainable future here on Earth. Furthermore, the pursuit of space exploration has always been a powerful catalyst for scientific and technological advancement. From the development of GPS and weather satellites to advancements in materials science and medical imaging, the benefits of space exploration extend far beyond the realm of astronomy and astrophysics. A sustained program of Mars exploration will undoubtedly lead to further breakthroughs that will benefit all of humanity. But the significance of Mars extends beyond mere survival and technological advancement. It touches upon something deeply fundamental to the human spirit, the drive to explore, to discover, and to push the boundaries of what is possible. Throughout history, humanity has been defined by its explorers, those who dared to venture into the unknown, to chart new territories, and to expand our understanding of the world. Mars represents the next great frontier, a new world to explore, to colonize, and to transform. It's an opportunity to create a new society, to build a better future, and to leave a lasting legacy for generations to come. And perhaps, most importantly, it's an opportunity to answer one of the most profound questions of all: are we alone in the universe? The search for life on Mars could revolutionize our understanding of biology and our place in the cosmos. Even if we don't find evidence of extant life, the discovery of past life on Mars would have profound implications for our understanding of the origins and evolution of life in the universe. The pursuit of this knowledge is a testament to our innate curiosity and our unwavering desire to understand the world around us. Mars isn't just a planet. It's a symbol of hope, a beacon of possibility, and a testament to the enduring spirit of human exploration. This course is designed to be a comprehensive exploration of the challenges and opportunities associated with establishing a permanent human presence on Mars. We will explore the scientific, technological, and societal considerations that are crucial for making this ambitious goal a reality. Over the next 12 chapters, we will journey from the initial motivations for Martian colonization to the detailed planning and execution of a sustainable human settlement. We'll start by establishing the why, the compelling reasons that drive our exploration of the Red Planet, and then move on to the how, the practical considerations of building a self-sufficient colony. This isn't just a scientific undertaking. It's a holistic examination of everything from habitat design and resource utilization to psychological well-being and ethical considerations. The course is structured to be accessible to students from diverse backgrounds, regardless of their prior knowledge of space exploration or planetary science. While some basic scientific principles will be discussed, the emphasis will be on critical thinking, problem solving, and the application of interdisciplinary knowledge. Here's a brief overview of what we'll cover in the coming chapters. Following this introductory chapter, we'll examine the geological history of Mars, its atmosphere, and the availability of vital resources such as water and minerals. We'll then move on to discuss the challenges of space travel, including radiation protection, propulsion systems, and life support technologies. A significant portion of the course will be dedicated to the design of sustainable Martian habitats, focusing on closed-loop systems for food production, water recycling, and waste management. We'll also explore the psychological and social challenges of living in a confined, isolated environment and the strategies for maintaining the well-being of a Martian colony. Furthermore, we'll delve into the ethical considerations of planetary colonization, including the preservation of potential Martian life and the responsible use of Martian resources. Throughout the course, we'll utilize case studies, simulations, and real-world examples to illustrate the complexities and challenges of Martian colonization. This course isn't merely about the technical aspects of Martian colonization. It's about envisioning a future where humanity has become a multi-planetary species. It's about inspiring the next generation of scientists, engineers, and explorers to tackle the challenges that lie ahead. And it's about fostering a sense of hope and optimism for the future of humanity. Throughout this course, you'll be encouraged to think critically, to ask questions, and to challenge assumptions. You'll be presented with complex problems and asked to develop innovative solutions. And you'll have the opportunity to collaborate with your peers and share your ideas. So, prepare to embark on a journey of discovery, innovation, and inspiration. Welcome to Can Mars Become Our Home? Let's begin to explore the possibilities of a new world. Our fascination with Mars stretches back millennia. While modern scientific exploration is relatively recent, the Red Planet has captivated humanity for centuries. In ancient times, Mars was often associated with war and conflict due to its reddish hue, which reminded observers of blood. The Romans named the planet after their god of war, and similar associations existed in other cultures. However, it wasn't until the advent of the telescope in the 17th century that we began to truly observe the surface of Mars. Astronomers like Galileo Galilei made early sketches of the planet, revealing rudimentary details of its surface features. But it was Giovanni Schiaparelli, in 1877, who made the observation that would ignite a century of Martian speculation. Schiaparelli observed what he believed to be linear features on the Martian surface, which he termed canali, channels. This term was mistranslated into English as canals, leading to the widespread belief that Mars was inhabited by intelligent beings who had constructed a network of waterways to irrigate their planet. This idea captured the public imagination and fueled a wave of Martian literature and speculation. Percival Lowell, a wealthy Bostonian astronomer, became the most prominent advocate for the existence of Martian canals. Lowell built an observatory in Flagstaff, Arizona, and spent years meticulously mapping the Martian surface, believing that the canals were evidence of a dying civilization desperately trying to conserve water. His book, Mars, published in 1908, became a bestseller and further popularized the idea of a habitable Mars. While Lowell's observations and interpretations were ultimately proven incorrect, his work played a significant role in inspiring generations of scientists and science fiction writers. The early 20th century saw a continued fascination with Mars, fueled by speculative literature and popular culture. Edgar Rice Burroughs' Barsoom series, which depicted a vibrant and adventurous Mars, captured the imagination of millions. However, as technology advanced, astronomers began to realize that the canals were likely optical illusions or misinterpreted features of the Martian surface. The era of modern Martian exploration began in the 1960s with the launch of several robotic probes. The first successful flyby of Mars was achieved by Mariner 4 in 1965. The images sent back by Mariner 4 shattered the romantic illusions of a habitable Mars, revealing a desolate and cratered landscape. These images were a stark contrast to the visions of lush gardens and flowing canals that had captivated the public imagination for decades. However, despite the disappointing results, the Mariner missions provided valuable data about the Martian atmosphere, surface features, and magnetic field. The Viking program, launched in the 1970s, consisted of 2 orbiters and 2 landers. The Viking landers conducted a series of experiments to search for evidence of life on Mars. While the results were inconclusive, the Viking missions provided a wealth of data about the Martian soil, atmosphere, and climate. The subsequent decades have seen a continued series of robotic missions to Mars, including the Mars Pathfinder, Spirit, Opportunity, Curiosity, and Perseverance rovers. These missions have revealed a more complex and intriguing Mars than previously imagined, with evidence of past water activity, organic molecules, and potentially habitable environments. The historical context of Martian exploration is a testament to our enduring curiosity and our relentless pursuit of knowledge. From the ancient astronomers who first gazed upon the red planet to the modern robotic probes that are exploring its surface, we have always been fascinated by the possibility of life beyond Earth. Let's begin our exploration of Mars by considering its geological structure. Unlike Earth, Mars lacks the same kind of actively shifting tectonic plates. This means its geological history unfolded quite differently. Early Mars, billions of years ago, was volcanically active. The Tharsis Bulge, a massive volcanic plateau, is a prime example. It's so large, roughly the size of North America, that it significantly altered the planet's gravity and shape. This bulge is home to Olympus Mons, the largest volcano and highest known mountain in our solar system. Its gentle slopes were formed by lava flows that were less viscous than those on Earth, allowing them to spread out over vast distances. The absence of plate tectonics also means that impact craters remain remarkably well preserved on the Martian surface, offering a window into the early bombardment history of the solar system. Unlike Earth, Where erosion and geological activity have erased many ancient craters, Mars provides a more complete record. Now, let's talk about the materials that make up Mars. The Martian crust is primarily composed of basalt, a volcanic rock rich in iron and magnesium. This is why Mars appears reddish. The iron oxide, or rust, on the surface gives it that characteristic color. The crust is thicker in the southern hemisphere, suggesting it's older and more heavily cratered. The northern hemisphere, in contrast, is smoother and younger, potentially resurfaced by ancient lava flows or massive impacts. Beneath the crust lies the mantle, which is thought to be solid and rocky, and at the core we have a dense metallic nucleus, likely composed of iron, nickel, and sulfur. However, unlike Earth, Mars's core is believed to be partially or entirely liquid, contributing to the planet's weak magnetic field. This weak field offers limited protection from harmful solar radiation, which has implications for any potential future colonization efforts. We know about this composition through studying meteorites originating from Mars, as well as data gathered by orbiting spacecraft and rovers. A key aspect of Mars's geological history is the evidence of past water activity. Numerous features, such as ancient riverbeds, lake basins, and outflow channels, suggest that liquid water once flowed abundantly on the planet's surface. The Valles Marineris, a colossal canyon system, is often compared to Earth's Grand Canyon, but it's far larger and more complex. Its formation may have involved both tectonic activity and erosion by ancient rivers and groundwater. Another compelling piece of evidence is the presence of hydrated minerals that contain water molecules in their crystal structure. These minerals have been detected by orbiting spacecraft and rovers, providing further confirmation that water played a significant role in shaping the Martian landscape. The question of where all the water went remains a subject of ongoing research, but it's likely that much of it was lost to space due to the planet's weak gravity and lack of a strong magnetic field. Some may also be locked up as ice in the polar regions and subsurface permafrost. Let's now shift our attention to the Martian atmosphere. It's dramatically different from Earth's. Much thinner, about one of Earth's atmospheric pressure. This thin atmosphere is primarily composed of carbon dioxide, about 96, with small amounts of argon, nitrogen, and traces of oxygen and water vapor. This composition traps very little heat, resulting in frigid temperatures. The average temperature on Mars is around 62 degrees Celsius, 80 degrees Fahrenheit, but it can vary significantly depending on the location and time of year. The atmospheric density is so low that even with a strong wind, it wouldn't feel very forceful to us. In fact, the most powerful winds on Mars are associated with dust storms, which can sometimes engulf the entire planet. Dust storms are a defining feature of the Martian climate. They can range in size from localized events to planet-encircling storms that last for months. These storms are driven by solar heating and atmospheric turbulence. Dust particles absorb sunlight, warming the atmosphere and creating temperature gradients that drive wind currents. The dust also affects the amount of sunlight reaching the surface, influencing temperatures and potentially impacting any future solar-powered infrastructure. It also poses a challenge for rovers and landers, as dust can accumulate on their solar panels and equipment, reducing their efficiency and potentially causing malfunctions. While dust storms are dramatic, they're also a natural part of the Martian climate and play a role in redistributing heat and dust across the planet. Mars experiences distinct seasons, much like Earth, due to its axial tilt. However, the Martian year is almost twice as long as Earth's, about 687 Earth days. This means that the seasons are longer and more drawn out. During the Martian summer, the polar ice caps shrink, releasing water vapor and carbon dioxide into the atmosphere. These gases contribute to a temporary increase in atmospheric pressure and temperature. During the winter, the ice caps expand, and carbon dioxide freezes out of the atmosphere, forming dry ice deposits. The Martian poles are composed primarily of water ice, but they also contain significant amounts of dust and carbon dioxide ice. These polar deposits represent a potential source of water for any future human settlements, but accessing and utilizing this resource would pose significant challenges. The question of whether water exists on Mars, and whether it existed in the past, is central to our understanding of the planet's potential habitability. As we've discussed, there's abundant evidence of past water activity, ancient riverbeds, lake basins, and hydrated minerals. But what about present-day water? For a long time, it was believed that all surface water had long since evaporated or frozen. However, recent discoveries have revealed compelling evidence of liquid water existing beneath the Martian South Polar ice cap. Radar data collected by the Mars Express spacecraft suggests the presence of a subsurface lake, potentially briny, meaning it contains dissolved salts, which lowers its freezing point. The discovery of this subsurface lake was a significant breakthrough, but it also raised many questions. The water is believed to be extremely cold and salty, making it unlikely to support life as we know it. However, it does demonstrate that liquid water can exist in stable conditions beneath the Martian surface, even in the harsh polar environment. Scientists are continuing to investigate the properties of this subsurface lake and search for other potential sources of liquid water on Mars. Another area of interest is the presence of recurring slope lineae, dark, narrow streaks that appear on steep slopes during the warmer months and then fade away during the winter. These features may be caused by flowing brine or shallow subsurface water. The search for water on Mars isn't just about understanding the planet's past. It's also about assessing its potential for supporting life. Water is essential for all known forms of life, and the presence of liquid water is considered a key indicator of habitability. While the Martian surface is currently inhospitable to most forms of life, there's a possibility that microbial life could exist in subsurface environments, protected from radiation and extreme temperatures. These subsurface environments could include underground aquifers, caves, or hydrothermal vents. Future missions to Mars will focus on exploring these subsurface environments and searching for evidence of past or present life. The discovery of water on Mars has profound implications for our understanding of the planet and our place in the universe. Mars, while captivating, presents a significant radiation challenge to any potential inhabitants. Unlike Earth, Mars lacks a global magnetic field and a substantial atmosphere. On Earth, our magnetic field deflects much of the harmful solar and cosmic radiation, and our atmosphere absorbs a good portion of what gets through. Mars, however, receives direct bombardment from these energetic particles. This isn't just a concern for astronauts during transit. It's a constant, pervasive threat for anyone living on the surface long term. We're talking about radiation that can damage DNA, increasing the risk of cancer, cataracts, and even neurological disorders. The radiation environment on Mars is roughly 70 to 100 times higher than on Earth. Now, it's important to differentiate between different types of radiation. We have solar particle events, bursts of energetic particles from the Sun, and galactic cosmic rays, which originate from outside our solar system. Both pose risks, but cosmic rays are particularly difficult to shield against due to their high energy. So, how do we protect ourselves? Shielding is the primary strategy. The most straightforward approach is to bury habitats underground, or to construct them using Martian regolith, the loose surface material. Regolith is surprisingly effective at blocking radiation, although a significant layer is required. Several meters of regolith can reduce radiation exposure to levels comparable to Earth. Another promising material is water. Water is an excellent radiation shield. Unfortunately, there's evidence of water ice on Mars, potentially accessible for shielding purposes. We could even create water walls around habitats. A more advanced concept involves using magnetic fields. By creating a localized magnetic field around a habitat, we could deflect charged particles, mimicking Earth's magnetic field on a smaller scale. This is a technologically challenging approach, but it offers a potentially very effective solution. Another approach is to leverage materials containing hydrogen, as hydrogen nuclei are effective at slowing down neutrons, a component of cosmic radiation. Beyond structural shielding, personal protection will be crucial. Specialized suits with integrated radiation shielding will be necessary for extravehicular activities, like exploring the surface or maintaining equipment. These suits will need to be lightweight, flexible, and provide adequate protection against both solar and cosmic radiation. Furthermore, continuous monitoring of radiation levels is essential. We'll need sophisticated sensors to track radiation exposure and provide warnings of impending solar events. These sensors could be integrated into habitats, suits, and rovers. Predictive modeling of solar activity will also be crucial. By forecasting solar flares and coronal mass ejections, we can provide advance warning and allow people to take shelter. It's also important to remember that radiation exposure is cumulative. Prolonged exposure, even at low levels, can have long-term health consequences. Therefore, careful planning and mitigation strategies are vital to ensure the safety of Martian inhabitants. Mars has about 38 of Earth's gravity. While this might sound appealing, less strain on your joints, the ability to jump higher, it presents a host of physiological challenges. Our bodies are adapted to Earth's gravity. Everything from our skeletal structure to our cardiovascular system relies on it. In low gravity, our muscles and bones begin to weaken. Without the constant stress of supporting our weight, they lose mass and density. This is similar to what happens to astronauts during extended space missions. But on Mars, the effect would be long-term and potentially irreversible. Our cardiovascular system also suffers. On Earth, gravity pulls blood downwards, requiring our hearts to work against it to pump blood to the brain. In low gravity, blood tends to pool in the upper body, leading to a decrease in blood pressure and a weakening of the heart muscle. The fluid shift also affects vision, potentially causing blurred vision and even permanent vision impairment. To counteract these effects, rigorous exercise will be essential. We'll need to develop exercise regimens specifically designed to maintain bone density and muscle mass in low gravity. This will likely involve resistance training, using specialized equipment to simulate the effects of gravity. Artificial gravity, while technologically challenging, could be a long-term solution. Rotating habitats or centrifuges could generate artificial gravity, mitigating the physiological effects of low gravity. However, these technologies are expensive and complex. Another approach is to use pharmaceutical interventions. Certain medications can help to slow down bone loss and muscle atrophy. However, these medications may have side effects, and their long-term effectiveness is uncertain. Beyond the musculoskeletal and cardiovascular systems, low gravity can also affect the immune system, potentially weakening our ability to fight off infections. Furthermore, the vestibular system, which controls balance and spatial orientation, will be significantly affected. Our brains are accustomed to processing sensory information in Earth's gravity. In low gravity, this information is distorted, leading to disorientation and difficulty with coordination. This can manifest as dizziness, nausea, and difficulty with fine motor skills. To address this, we'll need to develop training programs to recalibrate the vestibular system. This might involve using virtual reality simulations to create artificial gravity environments. Sensory reweighting techniques, which involve shifting our reliance from one sense to another, could also be helpful. Ultimately, living on Mars will require a fundamental shift in how we view physical fitness. Regular exercise, specialized training programs, and potentially even pharmaceutical interventions will be essential to maintain our health and well-being in a low-gravity environment. It won't be enough to simply be in shape by Earth standards. We'll need to be specifically adapted to the Martian environment. Mars is notorious for its dust storms. These aren't your typical Earth dust storms. They can grow to encompass the entire planet, lasting for months. Martian dust is incredibly fine and abrasive, composed of iron oxide. That's what gives Mars its reddish hue. These dust storms pose a multitude of hazards. First, there's the visibility issue. During a major dust storm, visibility can drop to near zero, making it impossible to navigate or operate equipment. Second, the dust can infiltrate habitats and equipment, causing mechanical failures and health problems. The fine particles can clog air filters, damage sensitive electronics, and irritate the lungs. Third, dust storms can reduce the efficiency of solar panels, which are a crucial source of power on Mars. To mitigate these hazards, habitats will need to be dust-tight. This requires robust sealing mechanisms and advanced air filtration systems. Regular cleaning of solar panels will be essential, either manually or using robotic cleaning systems. Designing habitats with aerodynamic shapes can help to reduce dust accumulation. Furthermore, we'll need to develop dust mitigation strategies for extravehicular activities. This might involve using specialized suits with dust-resistant coatings and airlocks with efficient dust removal systems. Dust storms aren't the only environmental hazard on Mars. Temperature fluctuations are extreme, ranging from as high as 70 degrees Fahrenheit to as low as 220 degrees Fahrenheit. This can cause materials to expand and contract, leading to stress fractures and failures. To address this, materials used in construction will need to be able to withstand these extreme temperature fluctuations. Utilizing materials with low thermal expansion coefficients and designing habitats with thermal insulation can help to minimize stress and prevent failures. Another hazard is the lack of a substantial atmosphere. The thin Martian atmosphere provides little protection from micrometeoroids, tiny space rocks that can damage habitats and equipment. Shielding habitats with protective layers can help to mitigate this risk. Ultimately, living on Mars will require a proactive and comprehensive approach to environmental hazard mitigation. Careful planning, robust engineering, and ongoing monitoring will be essential to ensure the safety and well-being of Martian inhabitants. Our journey towards establishing a permanent presence on Mars isn't about simply transporting everything we need from Earth. That's a logistical nightmare, frankly. It's astronomically expensive and, long-term, unsustainable. Instead, the key lies in in-situ resource utilization, or ISRU as we call it. This rather unwieldy term simply means learning to live off the land, to use the resources that Mars already offers. Think of it as a cosmic form of self-sufficiency. Earth's early explorers faced similar challenges. They didn't carry entire forests with them. They built shelter from the trees around them. Mars presents a similar, albeit more extreme, set of circumstances. ISRU isn't just a clever idea, it's a fundamental requirement for any long-term Martian settlement. It drastically reduces the mass we need to launch from Earth, lowering costs and increasing mission feasibility. And it opens the door to genuine independence, allowing us to build a thriving civilization without being perpetually reliant on supplies from home. We're not just visiting Mars, we're aiming to build on Mars. ISRU is the foundation of that building process. What exactly are these Martian resources we can utilize? Several stand out as particularly promising. The Martian atmosphere, for example, is about 96 carbon dioxide. While not breathable for us, it's a treasure trove of carbon and oxygen, elements crucial for creating fuel, plastics, and even breathable air. Martian regolith, the loose surface material, contains various minerals, including iron, silicon, aluminum, and magnesium. These can be extracted and used for construction, manufacturing, and even 3D printing. And, perhaps most importantly, there's evidence of significant water ice deposits, particularly in the polar regions and beneath the surface. Water, of course, is essential for life support, agriculture, and producing rocket fuel. The challenge isn't simply finding these resources, it's developing the technologies to efficiently extract, process, and utilize them. That's where a lot of current research and development is focused. We're looking at everything from atmospheric processes that can separate carbon dioxide into its constituent elements, to robotic mining systems that can excavate water ice, and advanced 3D printing techniques that can create habitats and tools from Martian materials. The logistical hurdles are substantial, of course. Extracting resources on Mars isn't as simple as it sounds. The atmosphere is thin, temperatures fluctuate wildly, and dust storms can engulf entire regions. We need robust, reliable equipment that can withstand these harsh conditions and operate autonomously, with minimal human intervention. The energy requirements are also significant. Extracting and processing resources takes power, and we'll need to generate that power sustainably, using solar, wind, or potentially even nuclear energy. But these are challenges we can overcome with careful planning, innovative engineering, and a willingness to invest in the necessary technologies. ISRU isn't just a technical problem, it's a paradigm shift. It requires us to rethink our approach to space exploration and to embrace a more sustainable, self-reliant model. It's about building a future where humanity can thrive not just on Earth, but on other worlds as well. Water is arguably the single most critical resource on Mars. It's essential for life support, providing drinking water, oxygen, and growing food. But it's also a valuable feedstock for producing rocket fuel through a process called electrolysis. Electrolysis uses electricity to split water molecules into hydrogen and oxygen. The hydrogen and oxygen can then be liquefied and used as propellant for rockets, allowing us to launch missions back to Earth or explore other parts of the solar system. So, finding and accessing water on Mars isn't just about survival, it's about enabling further exploration and expansion. The good news is that there's growing evidence of significant water ice deposits on Mars. These are primarily located in the polar regions, where ice caps and glaciers are known to exist. But there's also evidence of subsurface ice deposits at lower latitudes, buried beneath layers of regolith. These subsurface deposits are particularly promising, as they're more accessible and less susceptible to sublimation, the process where ice turns directly into vapor. Extracting water from Martian ice isn't as simple as drilling a hole and pumping it out. The ice is often mixed with regolith and other materials, and the surrounding ground can be extremely cold and hard. We'll need specialized drilling equipment, that can penetrate the frozen ground and extract the ice efficiently, and we'll need to develop processes for separating the water from the regolith and purifying it to make it safe for drinking and other uses. Several techniques are being considered for water extraction and purification. One approach involves using heat to melt the ice and vaporize the water, which can then be condensed and collected. Another approach involves using microwave energy to heat the ice and extract the water. And a third approach involves using chemical solvents to dissolve the ice and separate the water from the regolith. Once the water has been extracted and purified, it needs to be stored and distributed safely. This will require the construction of storage tanks, pipelines, and other infrastructure, and it will also require careful monitoring to ensure that the water remains clean and free of contamination. Beyond drinking water and rocket fuel, water will be crucial for agriculture. Growing food on Mars will be essential for providing a sustainable source of nutrition for a long-term colony, and water will be the key ingredient. We can't simply rely on transporting food from Earth indefinitely. It's too expensive and unsustainable. We'll need to develop closed-loop agricultural systems that can recycle water and nutrients, minimizing waste and maximizing efficiency. Hydroponics and aeroponics, growing plants without soil, are particularly promising techniques for Martian agriculture. These systems use significantly less water than traditional farming methods, and they can be easily adapted to the Martian environment. And they can be integrated with water recycling systems, creating a truly sustainable food production system. Ultimately, water is the lifeblood of any Martian colony. It's a resource we must carefully manage and conserve, and it's a resource that will enable us to not only survive on Mars, but to thrive. Growing plants directly in Martian regolith presents significant challenges. While regolith contains some essential nutrients, it's also lacking in organic matter and contains potentially harmful chemicals, like perchlorates. Perchlorates are salts that can be toxic to humans and plants, and they need to be removed or neutralized before regolith can be used for agriculture. Furthermore, Martian regolith has a poor structure for plant growth. It's compacted and doesn't retain water well. So, simply planting seeds in raw regolith is unlikely to be successful. We need to create a Martian soil that is suitable for plant growth. This involves amending the regolith with organic matter, neutralizing harmful chemicals, and improving its structure. One approach to creating Martian soil is to compost organic waste. Organic waste can be generated from a variety of sources, including food scraps, plant debris, and even human waste. Composting breaks down the organic matter into nutrient-rich humus, which can be mixed with the regolith to improve its fertility and structure. However, composting on Mars presents some unique challenges. The Martian atmosphere is thin and cold, which can slow down the composting process, and we'll need to ensure that the composting process is contained to prevent the spread of harmful microorganisms. Another approach to creating Martian soil is to use artificial nutrients. Artificial nutrients can be manufactured on Mars using locally available resources, and they can be added to the regolith to provide the essential nutrients that plants need to grow. Ultimately, creating Martian soil is about more than just providing nutrients. It's about creating a healthy ecosystem that supports plant growth. This involves fostering the growth of beneficial microorganisms in the soil, improving its water retention capacity, and providing a stable physical structure for plant roots. By carefully amending the regolith and fostering a healthy ecosystem, we can create Martian soil that is capable of supporting a thriving agricultural system. This will be essential for providing a sustainable food source for a long-term Martian colony, and it will be a testament to our ability to adapt and thrive in a new and challenging environment. As we contemplate establishing a long-term presence on Mars, the very first step involves thinking about where we'll live. This seems simple enough, but the Martian environment presents unique challenges. Unlike building a home on Earth, we can't simply rely on readily available materials or familiar construction techniques. We need to consider everything: radiation shielding, temperature regulation, structural integrity against dust storms, and even psychological well-being. Consequently, a range of habitat types are being proposed, each with its own advantages and disadvantages. Broadly, these fall into a few key categories: surface habitats, subsurface habitats, also known as lava tubes, and even inflatable habitats. Surface habitats, like the dome we see visualized, are the most straightforward to construct, but require substantial shielding. Think of them as building a house, but needing to protect against constant cosmic radiation and micrometeoroid impacts. Subsurface habitats, utilizing natural lava tubes, offer excellent inherent radiation protection and temperature stability, but present challenges in terms of access, exploration, and modification. And finally, inflatable habitats offer a lightweight and rapidly deployable solution, but are vulnerable to punctures and require a protective shell. Each of these types dictates, to a large extent, the materials we'll need to employ. Now, let's talk materials. Transporting everything we need from Earth is incredibly expensive and impractical. Therefore, maximizing the use of in situ resource utilization, ISRU, is paramount. This means using Martian resources to build and sustain our habitats. The most abundant resource on Mars is regolith, the loose surface material covering the planet. However, raw regolith isn't very useful on its own. It needs to be processed and combined with binders to create something structurally sound. One promising approach is regolith concrete, essentially Martian dust mixed with a binder, potentially sulfur, polymers created from Martian atmosphere, or even water ice if we can reliably extract it. This concrete can then be used to 3D print structures, build walls, or create shielding. Another area of research focuses on using basalt fibers, essentially Martian rock spun into threads, as a reinforcing material within the concrete, similar to rebar in Earth-based construction. This dramatically increases the strength and durability of the structures. Beyond regolith and basalt, we also need to consider materials for windows, seals, and life support systems. These might need to be transported from Earth initially, but the goal is to eventually find ways to manufacture them on Mars using ISRU as well. The way we actually build these habitats is also crucial. Traditional construction methods are simply not feasible on Mars. We need to rely heavily on automation and robotics. One particularly promising approach is 3D printing, also known as additive manufacturing. Using robotic arms and specialized nozzles, we can precisely deposit layers of regolith concrete, slowly building up walls, floors, and even entire structures. This offers several advantages. It minimizes waste, reduces the need for skilled labor, and allows for complex, customized designs. However, 3D printing on Mars isn't as simple as pressing a button. We need to develop robust, autonomous robots that can operate reliably in the harsh Martian environment. These robots need to be able to navigate challenging terrain, withstand extreme temperatures, and adapt to unexpected obstacles. Furthermore, the 3D printing process itself needs to be optimized for Martian conditions, taking into account the properties of regolith concrete and the planet's low gravity. Think of it as a fully automated construction crew, working tirelessly to build our new home with minimal human intervention. Let's dive deeper into the specifics of 3D printing. The process begins with characterizing the Martian regolith. determining its composition, particle size distribution, and mechanical properties. This is crucial for optimizing the concrete mix and ensuring its structural integrity. Next, we need to develop a binder that can effectively bind the regolith particles together. As we discussed, sulfur, polymers derived from the Martian atmosphere, or even water ice are all potential candidates. Once we have the concrete mix, it's fed into a 3D printer, which precisely deposits layers of material following a pre-programmed design. The printer needs to be equipped with sophisticated sensors and control systems to ensure accurate and consistent deposition. It also needs to be able to adapt to variations in the regolith and environmental conditions. A key challenge is dealing with the low gravity on Mars, which can affect the flow and adhesion of the concrete. We need to develop techniques to counteract these effects, such as using specialized nozzles or applying pressure to the deposited material. But 3D printing is just one piece of the puzzle. To build a truly sustainable habitat, we need a fully autonomous construction system. This means deploying a swarm of robots, each specializing in a particular task. Some robots might be responsible for excavating regolith, others for mixing concrete, and still others for 3D printing or assembling prefabricated components. These robots need to be able to communicate with each other, coordinate their actions, and adapt to changing conditions. This requires sophisticated artificial intelligence and machine learning algorithms. For example, robots might use computer vision to identify obstacles, map the terrain, and monitor the progress of construction. They might also use reinforcement learning to optimize their actions and improve their efficiency. The key is to create a self-organizing, resilient system that can operate independently with minimal human intervention. This is a significant technological challenge, but it's essential for establishing a long-term presence on Mars. Crucially, this autonomous system must also include inspection and maintenance capabilities. Once a habitat is constructed, robots need to continuously monitor its structural integrity, identify any cracks or weaknesses, and perform repairs as needed. This could involve using drones to inspect the exterior of the habitat, or deploying specialized robots to patch cracks or reinforce weak areas. The inspection process needs to be automated and reliable, as human intervention would be impractical and expensive. Furthermore, the system needs to be able to adapt to unforeseen circumstances, such as dust storms or micrometeoroid impacts. For example, robots might be able to automatically deploy protective shields or repair damaged sections of the habitat. The goal is to create a self-healing, resilient habitat that can withstand the harsh Martian environment and provide a safe and comfortable home for future explorers. Now, let's shift gears and discuss the most critical aspect of Martian habitats: life support. Unlike simply building a shelter, we need to create an environment that can sustain human life. This is far more complex than it sounds. On Earth, we rely on a vast, interconnected ecosystem to provide us with air, water, and food. On Mars, we need to recreate that ecosystem within our habitats. This requires a closed-loop life support system, a self-sustaining environment that minimizes waste and maximizes resource utilization. The core principle is to recycle everything. Air, water, and nutrients must all be recovered and reused. This is achieved through a combination of physical, chemical, and biological processes. For example, carbon dioxide exhaled by astronauts can be removed from the air and converted back into oxygen through electrolysis, or through the use of photosynthetic organisms like plants. One of the most important components of a closed-loop life support system is food production. Transporting enough food from Earth to sustain a long-term Martian colony is simply not feasible. Therefore, we need to grow our own food on Mars. Hydroponics and aeroponics are particularly well suited for this purpose. These techniques allow us to grow plants without soil, using nutrient-rich water solutions. They're highly efficient and require minimal space, making them ideal for enclosed habitats. We can also use algae and insects as protein sources. These are highly efficient converters of energy and require minimal resources to produce. However, growing food on Mars isn't without its challenges. We need to provide the plants with the right amount of light, water, and nutrients. We also need to protect them from radiation and maintain a stable temperature. And finally, we need to ensure that the food is safe and nutritious. Water recycling is another crucial component of a closed-loop life support system. Water is a precious resource, and transporting it from Earth would be prohibitively expensive. Therefore, we need to recycle as much water as possible. This includes recycling wastewater, urine, and even humidity from the air. The recycling process involves a series of purification steps, including filtration, distillation, and biological treatment. The purified water can then be reused for drinking, cooking, and agriculture. However, ensuring the purity of the recycled water is critical. We need to remove all contaminants, including bacteria, viruses, and chemical pollutants. This requires sophisticated purification technologies and rigorous monitoring. The goal is to create a closed-loop water system that is self-sustaining and reliable, providing a safe and sustainable source of water for future Martian explorers. Let's begin with the fundamentals of growing food without soil. On Mars, soil, as we know it, is problematic. It lacks the necessary nutrients and is potentially contaminated with perchlorates, which are harmful to humans. This is where hydroponics and aeroponics become vital. Hydroponics, at its core, is the method of growing plants using mineral nutrient solutions in water, without soil. Think of it as providing the plants with a perfectly balanced meal directly to their roots. The roots are either suspended in the nutrient solution or supported by an inert medium like gravel or rock wool. This allows for incredibly efficient water and nutrient use and faster growth rates. It's been used successfully on Earth for years and scales very well to contained environments, making it perfect for a Martian habitat. We're not reinventing the wheel, we're simply adapting proven technology to a new environment. Now, let's move on to aeroponics. Aeroponics takes the concept a step further. Instead of submerging the roots in water, the roots are suspended in air and periodically sprayed with a nutrient-rich solution. This provides even more oxygen to the roots, potentially leading to even faster growth rates and reduced water usage. Think of it like a fine mist constantly nourishing the plant. Both hydroponics and aeroponics can be integrated into a closed-loop system, where water and nutrients are recycled, minimizing waste and maximizing efficiency. This is critical on Mars, where resources are scarce. The challenge lies in maintaining the correct pH balance, preventing the growth of harmful bacteria, and ensuring consistent nutrient delivery. But these are engineering problems, and engineers are adept at solving problems. The design of these systems on Mars would likely favor vertical farming. Space is at a premium, so maximizing the growing area within a limited volume is essential. Vertical farms, utilizing stacked layers of hydroponic or aeroponic systems, can dramatically increase crop yields per square meter. Furthermore, these systems can be automated, with robots handling tasks like planting, harvesting, and monitoring plant health. This reduces the need for human labor, which is valuable on Mars. LED lighting will be crucial, providing the specific wavelengths of light that plants need for photosynthesis. The energy for these lights can be generated by solar panels, creating a sustainable and self-sufficient food production system. It's a complex undertaking, certainly, but entirely feasible with current technology. Let's broaden our food sources beyond traditional plants. While hydroponics and aeroponics provide a strong foundation, diversifying our diet is crucial for long-term sustainability and nutritional completeness. Enter insect farming. It sounds unusual to some, but insects are incredibly efficient at converting feed into protein. They require far less land, water, and feed than traditional livestock, and they have a much shorter life cycle. Crickets, mealworms, and black soldier fly larvae are all viable candidates for Martian insect farms. They can be fed on waste products from the hydroponic systems, creating a closed-loop system where one form of waste becomes another's food. It's a beautiful example of ecological efficiency. Now, the question arises, how do we make insects palatable? The answer lies in processing. Insects can be ground into flour, which can be used to make bread, pasta, and other baked goods. They can also be processed into protein bars, snacks, and even meat substitutes. The nutritional value is impressive. Insects are rich in protein, essential amino acids, and micronutrients. The psychological hurdle, of course, is real, but with careful presentation and marketing, we can overcome this challenge. Remember, many cultures around the world already consume insects as a traditional food source. We're simply introducing a sustainable and efficient protein source to a new environment. Beyond insects, we can also explore other alternative protein sources. Mycoprotein, derived from fungi, is another promising candidate. It's a highly sustainable and nutritious protein source that requires minimal land and water. Furthermore, research into lab-grown meat, also known as cultured meat, is rapidly advancing. This involves growing meat cells in a laboratory without the need for traditional animal agriculture. While still in its early stages, lab-grown meat has the potential to revolutionize food production, offering a sustainable and ethical alternative to conventional meat. The key is to diversify our protein sources, reducing our reliance on any single food item and creating a resilient and sustainable food system for Mars. Let's zoom out and consider the bigger picture. The ultimate goal is to create a truly closed-loop ecosystem, where waste from one process becomes the input for another. This minimizes the need for external resources and creates a sustainable and self-sufficient food production system. Think of it as a miniature version of Earth's biosphere, contained within a Martian habitat. Waste from the hydroponic systems, such as plant trimmings and nutrient-rich water, can be used to feed insects. Insect waste can then be used as fertilizer for the plants. Human waste can be processed and used as a source of nutrients for both plants and insects. This creates a circular flow of resources, reducing waste and maximizing efficiency. The key to success lies in meticulous planning and integration. We need to carefully balance the inputs and outputs of each component of the system. For example, the amount of waste generated by the human inhabitants needs to be matched by the capacity of the plants and insects to process it. The water recycling system needs to be efficient enough to minimize water loss. The air purification system needs to remove harmful pollutants and maintain a breathable atmosphere. This requires a holistic approach, considering all aspects of the ecosystem and optimizing them for efficiency and sustainability. This isn't just about growing food, it's about creating a life support system that can sustain a human colony on Mars for generations to come. Ultimately, the goal is not just to survive on Mars, but to thrive. By creating a closed-loop ecosystem, we can create a sustainable and self-sufficient food production system that can support a human colony for generations to come. This requires a commitment to innovation, collaboration, and a deep understanding of the interconnectedness of all living things. It's a challenging undertaking, certainly, but one that is within our reach, and the rewards, a sustainable future for humanity on another planet, are immeasurable. It's a testament to our ingenuity, our resilience, and our unwavering spirit of exploration. Our journey to making Mars our home fundamentally relies on our ability to move across its surface. For now, that means relying on robotic explorers, surface rovers and robots. These aren't just about driving around, they're about scientific investigation, resource mapping, and, crucially, reconnaissance for future human settlements. The earliest rovers, like Sojourner, were proof-of-concept vehicles. They showed us it could be done. But the later generations, Spirit, Opportunity, Curiosity, and Perseverance, represent leaps in capability. They're essentially mobile science laboratories. Consider Curiosity, for example. It's equipped with a suite of instruments, cameras for detailed imaging, spectrometers to analyze the chemical composition of rocks and soil, and drills to collect samples from beneath the surface. This isn't just about finding evidence of past or present life, though that is a significant goal. It's about understanding the geological history of Mars, identifying potential resources like water ice, and assessing the habitability of different locations. These rovers are painstakingly slow. They rarely exceed walking speed, but that's a trade-off for their robustness and power efficiency. Martian terrain is notoriously challenging, rocky, sandy, and often riddled with hidden obstacles. The rover's wheels and suspension systems are designed to cope with these challenges, but even so they require careful planning and remote operation by teams of engineers on Earth. But rovers aren't just about autonomous exploration. They're also critical for scouting locations for future habitats and resource utilization. Before we send humans to Mars, we need to know where we can find water ice, build shelters, and generate power. Rovers can map these resources, analyze their composition, and assess their accessibility. This is where the concept of in-situ resource utilization, or ISRU, comes into play. ISRU is about using the resources available on Mars to create the things we need to survive, rather than having to transport everything from Earth. For example, water ice can be extracted and used to produce water, oxygen, and rocket fuel. Rovers can identify promising locations for ISRU facilities and assess the feasibility of extracting these resources. Furthermore, advancements in robotics are leading to the development of more specialized robots for specific tasks. We're seeing robots designed for construction, habitat building, and even agriculture. These robots could work alongside humans to create a self-sustaining Martian colony. The key is to develop robots that are robust, reliable, and capable of operating autonomously or with minimal human intervention. However, rovers have limitations. Their speed, range, and power capacity are all constrained, and they can only collect a limited amount of data. This is where the next generation of Martian mobility solutions comes into play: pressurized rovers and habitats. Imagine a rover that's not just a scientific instrument, but a mobile home, a pressurized vehicle that can carry humans across the Martian surface for extended periods. These pressurized rovers would allow astronauts to explore a much larger area, conduct more complex research, and live and work in a comfortable and safe environment. They would need to be equipped with life support systems, power generators, and communication equipment, and they would need to be robust enough to withstand the harsh Martian environment, including extreme temperatures, radiation, and dust storms. Building these pressurized rovers is a significant engineering challenge, but it's a challenge that's well within our capabilities, and it's a crucial step towards establishing a permanent human presence on Mars. Pressurized rovers aren't just about transportation, they are about extending the reach of human exploration and enabling longer duration missions. Think of them as mobile habitats, capable of supporting a small crew for weeks or even months. This requires a complete life support system, oxygen regeneration, carbon dioxide removal, water recycling, and waste management. These systems are complex and energy intensive, but they are essential for maintaining a habitable environment inside the rover. Moreover, the rover must be shielded from radiation, which is a significant hazard on Mars. This can be achieved through the use of specialized materials and shielding technologies. The design of a pressurized rover also needs to consider ergonomics and habitability. Astronauts will be spending long periods inside the rover, so it's important to create a comfortable and functional living space. This includes providing adequate space for sleeping, eating, working, and exercising. Furthermore, the rover must be equipped with communication equipment to maintain contact with Earth and other Martian assets. While pressurized rovers extend our mobility, permanent presence demands habitats. These aren't just shelters, they're self-sustaining ecosystems designed to support human life for years, decades, or even generations. One promising approach is to utilize Martian regolith, the loose surface material, as a building material. Regolith can be used to create bricks, concrete, or even 3D printed structures. This would significantly reduce the cost and complexity of transporting building materials from Earth. Another important consideration is radiation shielding. Mars lacks a global magnetic field and has a thin atmosphere, which means that the surface is exposed to high levels of radiation. Habitats can be shielded from radiation by burying them underground, constructing them from radiation-resistant materials, or using magnetic shielding technologies. The design of Martian habitats also needs to address the challenges of growing food, generating power, and managing waste. Hydroponics and aeroponics, growing plants without soil, are promising techniques for producing food on Mars. Solar power and nuclear power are potential sources of energy, and closed-loop life support systems, recycling water, air and waste, are essential for minimizing resource consumption. These habitats won't be isolated structures, however. We envision interconnected networks of habitats, linked by pressurized tunnels or rover routes. This would allow for collaboration, resource sharing, and mutual support. Furthermore, these habitats will need to be equipped with advanced communication systems to maintain contact with Earth and other Martian assets. Virtual reality and augmented reality technologies can also play a role in enhancing the quality of life for Martian colonists, providing access to entertainment, education, and social interaction. Ultimately, the goal is to create a self-sustaining Martian civilization capable of thriving independently of Earth. Earth requires not only advanced technology, but also a new mindset, a commitment to resourcefulness, collaboration, and long-term sustainability. Beyond surface mobility, unlocking the full potential of Martian exploration demands a third dimension: aerial exploration. Rovers are limited by terrain and line of sight, but drones, or aerial vehicles, can overcome these limitations. The Martian atmosphere is thin, about one of Earth's, which poses a challenge for conventional aircraft. However, drones with larger rotors and more powerful engines can generate enough lift to fly. These drones can be used for a variety of purposes: reconnaissance, mapping, surveying, and even sample collection. They can access areas that are inaccessible to rovers, providing a broader perspective on the Martian landscape. Furthermore, drones can be equipped with advanced sensors, such as high-resolution cameras, spectrometers, and LiDAR, to collect detailed data about the Martian environment. This data can be used to create accurate maps, identify potential hazards, and locate valuable resources. But the potential of drones goes beyond simple reconnaissance. We envision swarms of drones working together to perform complex tasks, such as constructing habitats, mining resources, and maintaining infrastructure. These drones could be equipped with robotic arms, 3D printing nozzles, and other tools to automate construction processes and reduce the need for human labor. Furthermore, drones could be used to create aerial networks, providing communication and data relay services for rovers, habitats, and other Martian assets. The coordination of these drone swarms will require advanced artificial intelligence and machine learning algorithms. The drones will need to be able to communicate with each other, share information, and adapt to changing conditions. They will also need to be able to operate autonomously without constant human intervention. One particularly promising area for drone exploration is subsurface environments, such as lava tubes and caves. These underground spaces offer protection from radiation and micrometeorites, and they may harbor evidence of past life. Drones can be equipped with specialized sensors to map these subsurface environments and search for signs of water, organic molecules, or microbial life. The exploration of these subsurface environments will require drones that are small, agile, and capable of navigating tight spaces. They will also need to be equipped with powerful lights and advanced sensors to overcome the challenges of operating in darkness and confined environments. Ultimately, the combination of surface mobility, aerial exploration, and subsurface investigation will unlock the full potential of Martian exploration, paving the way for a permanent human presence on the Red Planet. Establishing effective medical facilities on Mars is, naturally, paramount. It's not simply about replicating a terrestrial hospital. It's about building a self-sufficient system capable of handling everything from routine checkups to complex trauma, and even long-term health management in an entirely new environment. We need to consider the unique challenges. Supply chains will be vastly extended, making rapid resupply of pharmaceuticals and equipment difficult. Therefore, on-site manufacturing of essential medications using techniques like bioprinting and automated synthesis will be crucial. This isn't just about having a pharmacy, it's about being a pharmacy. Moreover, we must prioritize preventative medicine. Regular health monitoring, using advanced diagnostic tools, will allow us to identify and address potential problems before they become critical. This includes monitoring bone density loss due to lower gravity, assessing radiation exposure, and managing the psychological effects of isolation, which we'll discuss later. The facilities themselves will be modular and adaptable, designed to be expanded or reconfigured as the colony grows. Think of them as sophisticated, self-contained medical pods that can be connected and integrated seamlessly into the habitat. The role of automation and robotics in Martian medical care will be significant. Robotic surgeons, capable of performing complex procedures with precision and minimal invasiveness, will be essential, especially during emergencies. These robots can be remotely operated by surgeons on Earth, providing expert guidance when needed. Furthermore, AI-powered diagnostic tools can analyze medical data with incredible speed and accuracy, assisting doctors in making informed decisions. But it's not just about replacing human doctors, it's about augmenting their capabilities. The AI can handle routine tasks, freeing up doctors to focus on more complex cases and provide personalized care. Telemedicine will also play a crucial role, allowing Martian colonists to consult with specialists on Earth, share medical data, and receive remote guidance. Consider a scenario where a colonist develops a rare condition. Telemedicine can connect them with a leading expert on Earth, who can provide a diagnosis and recommend a treatment plan. This is particularly important given the limited number of medical professionals who will initially be stationed on Mars. Training colonists in basic medical skills will be another key component of our healthcare strategy. This will empower them to provide first aid, manage minor illnesses, and assist medical professionals during emergencies. And let's not forget the importance of nutrition in maintaining health on Mars. Access to fresh, locally grown food will be crucial. We'll need to establish closed-loop agricultural systems, utilizing hydroponics and aeroponics to grow fruits, vegetables, and grains within the habitat. This not only provides a sustainable source of food, but also ensures that colonists receive the essential vitamins and minerals they need to stay healthy. Furthermore, we can explore the potential of cultivating algae and insects as alternative protein sources. These are highly efficient and sustainable food sources that require minimal resources. The agricultural systems will be integrated with the habitat's waste management system, recycling water and nutrients to minimize waste and maximize efficiency. In essence, we're creating a self-sustaining ecosystem within the habitat, ensuring that colonists have access to a healthy and nutritious diet, even in the harsh environment of Mars. Maintaining a diverse and balanced diet is paramount for boosting immunity and preventing deficiencies. It's about more than just survival. It's about thriving on a new planet. The psychological challenges of long-duration space travel and living on Mars are significant. Isolation, confinement, and the lack of familiar social cues can have a profound impact on mental health. Imagine being millions of miles away from Earth, separated from family and friends, and confined to a small enclosed space. The constant awareness of danger, the lack of privacy, and the monotony of daily life can lead to stress, anxiety, depression, and even cognitive decline. It's crucial that we proactively address these challenges. Careful screening and selection of astronauts and colonists are essential. We need to identify individuals who are psychologically resilient, adaptable, and capable of coping with stress. But screening alone isn't enough. We need to provide ongoing psychological support, including regular counseling sessions, mindfulness training, and access to virtual reality environments that simulate Earth-like settings. These virtual environments can provide a sense of escape and help colonists maintain a connection to their home planet. Maintaining strong social connections is also vital. We need to create opportunities for colonists to interact with each other, share their experiences, and provide mutual support. This could involve regular group activities, team-building exercises, and virtual social events. Encouraging open communication and fostering a sense of community are essential. It's important to create a culture where colonists feel comfortable sharing their thoughts and feelings and seeking help when they need it. We also need to consider the impact of delayed communication with Earth. The significant time delay can make it difficult to maintain real-time conversations with family and friends. This can exacerbate feelings of isolation and loneliness. We need to develop strategies for mitigating this impact, such as pre-recorded messages, asynchronous communication tools, and virtual reality experiences that allow colonists to visit their loved ones. Providing opportunities for personal expression and creativity is also crucial. Colonists need to have outlets for their emotions and a way to maintain a sense of individuality. This could involve encouraging hobbies, such as painting, writing, music, or gardening. Providing access to books, films, and other forms of entertainment is also important. We should also consider the importance of environmental design. Creating a habitat that is aesthetically pleasing and comfortable can have a positive impact on mental health. This could involve incorporating natural elements, such as plants and natural light, into the design. Providing access to outdoor spaces, even if they are enclosed, can also be beneficial. In essence, we need to create a habitat that is not only functional, but also supportive of the psychological well-being of its inhabitants. It's about creating a home away from home. Maintaining physical fitness on Mars is not merely about aesthetics. It's essential for survival. The reduced gravity and the confined environment will have a significant impact on muscle mass, bone density, and cardiovascular health. Without regular exercise, colonists will experience muscle atrophy, bone loss, and a decline in overall physical function. This will not only affect their ability to perform essential tasks, but also increase their risk of injury. Therefore, establishing a comprehensive exercise program is paramount. This program should include a variety of activities, such as cardiovascular exercise, strength training, and flexibility exercises. Cardiovascular exercise can be achieved through running on a treadmill, cycling on a stationary bike, or swimming in a small pool. Strength training can be achieved through lifting weights, using resistance bands, or performing bodyweight exercises. Given the limited space within the habitat, we need to be creative in our approach to exercise. Virtual reality can play a significant role in this regard. By using VR headsets, colonists can simulate outdoor workouts, such as running through a forest, climbing a mountain, or cycling along a scenic road. This not only provides a more engaging and motivating workout experience, but also helps to combat the psychological effects of confinement. In addition to traditional exercise, we should also encourage colonists to incorporate physical activity into their daily routines. This could involve walking or cycling to work, taking the stairs instead of the elevator, or participating in team sports. The key is to make physical activity a habit rather than a chore. Furthermore, we should explore the development of specialized exercise equipment designed to mitigate the effects of reduced gravity. This could involve using centrifugal force or magnetic fields to create a simulated gravitational environment. Such equipment would allow colonists to perform exercises that would be difficult or impossible to perform in reduced gravity. Regular monitoring of physical fitness levels is also essential. This will allow us to identify any potential problems early on and adjust the exercise program accordingly. In essence, maintaining physical fitness on Mars requires a proactive and comprehensive approach. It's about ensuring that colonists have the resources, the equipment, and the motivation to stay healthy and active, even in the harsh and challenging environment of a new planet. When we contemplate establishing a permanent presence on Mars, one of the most significant challenges isn't the physical journey itself, but the sheer distance separating us from Earth. This distance directly impacts communication, introducing what we call latency, a delay in transmission. Now, imagine trying to have a real-time conversation with someone when every word you say takes minutes to reach them. That's the reality of Earth-Mars communication. depending on the relative positions of the two planets, and their orbits aren't perfectly circular, remember. The signal travel time can range from about 3 to 22 minutes each way. So, a simple hello and a response could easily take over 40 minutes. This isn't just an inconvenience, it fundamentally changes how we approach operations on Mars. Consider the implications. Real-time control of rovers or habitats becomes impossible. We can't simply drive a rover on Mars like we do here on Earth. Every command has to be pre-programmed and sent with the understanding that there will be a significant delay before receiving any feedback. This requires a high degree of autonomy in Martian systems. Robots and AI that can make decisions and react to situations without constant human intervention. Think of it like playing chess by mail. You send a move, wait for a response, and then send another. It's a very different game than playing face-to-face. The concept of ground control will have to evolve into a system that primarily monitors and verifies pre-programmed actions. To mitigate the effects of latency, communication protocols will need to be designed with this delay in mind. We'll need to prioritize information, what's absolutely critical to transmit immediately, and what can be stored and sent later. Techniques like data compression will be essential to maximize the amount of information we can send within limited bandwidth windows. Furthermore, we'll need to develop robust error correction methods to ensure that data isn't corrupted during transmission, given the vast distances involved. Imagine trying to send a complex scientific dataset across interplanetary space. A single error could render the entire transmission useless. Redundancy is key, meaning we'll likely need multiple communication channels to increase reliability. These channels will utilize different frequencies and technologies to provide backup in case of signal interference or equipment failure. Given the communication delays, relying solely on transmitting all data back to Earth isn't feasible. We'll need substantial on-site data storage capabilities on Mars. This isn't simply a matter of packing a few hard drives. It requires a comprehensive data management system. The sheer volume of data generated by scientific experiments, habitat monitoring, and daily operations will be enormous. We're talking about terabytes, potentially petabytes, of information accumulating every single day. Furthermore, this data needs to be reliably stored for extended periods, protected from radiation, extreme temperatures, and potential physical damage. Redundancy is again crucial. Multiple copies of critical data will need to be stored in geographically separated locations to ensure that no single event can result in data loss. Data organization is just as important as storage. We'll need sophisticated metadata tagging and indexing systems to allow researchers to quickly and efficiently locate specific information. Imagine sifting through petabytes of raw data without knowing what you're looking for. It would be like searching for a needle in a haystack. Furthermore, data compression techniques will be vital to reduce storage requirements and transmission times. Advanced algorithms will be needed to preserve data integrity while minimizing file sizes. Data lifecycle management is also critical. We'll need to establish policies for data retention, archival, and deletion to ensure that we're only storing information that is truly necessary. Finally, data security is paramount. Protecting sensitive scientific data and personal information from unauthorized access will be a major challenge. We'll need robust encryption protocols and access control mechanisms to safeguard against cyber attacks and data breaches. This will require ongoing vigilance and adaptation to evolving security threats. The entire data management system will need to be designed with resilience in mind, capable of withstanding potential failures and disruptions. Automated backups, fault-tolerant storage systems, and disaster recovery plans will be essential to ensure the long-term preservation of critical data. Essentially, the Martian base will need to operate as an information fortress. Given the limitations of communication and the sheer volume of data, artificial intelligence will be absolutely essential for operating a sustainable Martian base. AI won't just be a helpful tool, it will be a critical partner. We'll need AI systems capable of autonomously monitoring life support systems, managing power generation, and controlling environmental conditions within the habitat. Imagine an AI constantly analyzing sensor data, predicting potential failures, and taking corrective action before they occur. This level of proactive maintenance will be crucial for ensuring the safety and well-being of the crew. Furthermore, AI can assist with scientific research, analyzing complex data sets, identifying patterns, and formulating hypotheses. This can accelerate the pace of discovery and unlock new insights into the Martian environment. AI-powered decision support systems will be invaluable for addressing unexpected situations. When a problem arises, the AI can analyze available data, evaluate potential solutions, and recommend the best course of action. This can be particularly important when communication delays prevent immediate consultation with Earth-based experts. Furthermore, AI can assist with resource management, optimizing the use of limited supplies such as water, oxygen, and food. This is critical for ensuring the long-term sustainability of the base. Importantly, these AI systems won't operate in isolation. They'll need to be integrated with the overall data management system, allowing them to access and analyze relevant information in real time. This requires a sophisticated software architecture and robust data interfaces. Finally, AI can play a crucial role in automating routine tasks, freeing up the crew to focus on more complex and creative endeavors. This could include tasks such as monitoring equipment, collecting samples, and performing basic repairs. Furthermore, AI can assist with training and education, providing personalized learning experiences tailored to the needs of each crew member. As AI systems become more sophisticated, they may even be able to collaborate with the crew on scientific research, acting as intelligent assistants and co-investigators. The ultimate goal is to create a symbiotic relationship between humans and AI, leveraging the strengths of both to achieve a shared objective: the successful and sustainable exploration of Mars. Our journey to Mars isn't just about technological achievement. It's about a profound ethical responsibility. This leads us to the critical field of planetary protection. The core principle is simple: we must avoid both forward and backward contamination. Forward contamination refers to introducing terrestrial life to Mars, potentially disrupting any native ecosystems that might exist, however unlikely they may seem. Imagine a single bacterium thriving on Martian soil, altering the chemical composition and rendering any future search for indigenous life inconclusive. It's like trying to find a needle in a haystack that's been deliberately filled with more needles. We must sterilize everything we send: spacecraft, rovers, even the suits worn by astronauts, to minimize the risk. This isn't about fearing aliens, it's about preserving the integrity of another world's potential biosphere, allowing for a genuinely unbiased scientific investigation. The challenge is immense, as absolute sterilization is practically impossible, but we strive for the highest possible levels of cleanliness and employ techniques like heat treatment, radiation exposure, and the use of biocidal materials. Backward contamination presents a different, though equally serious risk. This concerns the potential for Martian life, if it exists, to be brought back to Earth and pose a threat to our own biosphere. While the probability of harmful Martian life is considered low, the consequences could be catastrophic. Imagine an organism, adapted to the harsh Martian environment, finding Earth's ecosystem an easy target. It's a scenario that science fiction has long explored, and while unlikely, we must take it seriously. This is why returned samples are subject to stringent quarantine protocols. They are initially contained within highly secure facilities, known as biosafety levels, designed to prevent any accidental release. These facilities feature multiple layers of containment, including airlocks, filtration systems, and specialized handling procedures. Samples are meticulously analyzed, first remotely using robotic systems, and then, if deemed safe, by human scientists wearing protective gear. The goal isn't to fear the unknown, but to proceed with caution and ensure the safety of our planet. Planetary protection isn't just about technology and procedures. It's a global effort requiring international cooperation. The Committee on Space Research (COSPAR) plays a crucial role in setting guidelines and standards for planetary protection. These guidelines are constantly evolving as our understanding of Mars improves and as new technologies emerge. There's often a delicate balance between scientific ambition and planetary protection concerns. Strict protocols can limit the scope of exploration, but they're essential to safeguarding both Mars and Earth. Ultimately, responsible exploration requires a commitment to minimizing risks, upholding ethical principles, and prioritizing the long-term health of our solar system. This isn't a constraint on progress, but a fundamental aspect of it. As we begin to seriously contemplate a permanent presence on Mars, the question of resource ownership becomes paramount. Mars is rich in resources: water, ice, minerals, and potentially even rare earth elements, all of which could be crucial for establishing a self-sustaining colony. But who has the right to exploit these resources? Current international law, specifically the Outer Space Treaty of 1967, prohibits national appropriation of celestial bodies. This means no single country can claim sovereignty over Mars or any part of it. However, the treaty is somewhat ambiguous regarding the extraction and use of resources. While it prohibits claiming ownership, it doesn't explicitly forbid utilizing resources for in situ resource utilization (ISRU), the practice of using Martian resources to support a Martian colony. This ambiguity has led to a lively debate among legal scholars and policymakers. Some argue that ISRU is permissible under the treaty as long as it's done for peaceful purposes and benefits all of humanity. They propose a system of common heritage of mankind, where resources are shared equitably. Others contend that any extraction of resources constitutes appropriation and is therefore prohibited. They suggest a licensing system where companies or countries can obtain permits to extract resources in exchange for royalties or other benefits. The US has already passed legislation, the Space Act of 2015, which grants US citizens the right to own resources they extract from asteroids and other celestial bodies, although the legality of this act under international law remains questionable. Establishing a clear and internationally accepted legal framework for space resource utilization is crucial to avoid conflicts and ensure the sustainable development of Mars. It requires a delicate balance between encouraging innovation, protecting the Martian environment, and ensuring equitable access to resources. A potential solution could involve establishing an international regulatory body to oversee resource extraction, enforce environmental standards, and distribute benefits fairly. This body could also be responsible for resolving disputes and ensuring compliance with international law. The future of Martian colonization depends not only on our technological capabilities, but also on our ability to create a just and sustainable legal framework for the use of its resources. Beyond the legal and economic challenges, we must also consider the social and political structure of a Martian colony. What form of governance will be most effective? Will it be a direct democracy, a representative democracy, or something else entirely? The unique challenges of living on Mars, isolation, limited resources, and the need for collective survival will likely necessitate a different approach than what we're accustomed to on Earth. Traditional political systems may not be well suited to the harsh realities of Martian life. A highly centralized, technocratic governance structure focused on efficiency and survival might be more appropriate, at least in the initial stages of colonization. However, this raises concerns about individual liberties and the potential for authoritarianism. Another crucial consideration is social cohesion. How can we create a community that is resilient, equitable, and inclusive? The initial colonists will likely be a small, highly selected group with a shared purpose. However, as the colony grows, it will become more diverse. Managing this diversity and preventing social stratification will be essential. Establishing clear ethical guidelines, promoting social justice, and ensuring equal access to resources will be crucial. A strong sense of community identity and shared values will also be important in fostering social cohesion. The selection process for initial colonists should prioritize not only technical skills but also social intelligence, emotional maturity, and the ability to work effectively in a team. Ultimately, the success of a Martian colony will depend not only on our technological prowess, but also on our ability to create a just, sustainable, and thriving society. It requires careful planning, thoughtful governance, and a commitment to ethical principles. We must learn from the mistakes of the past and create a new model for human civilization, one that is resilient, equitable, and capable of adapting to the challenges of a new world. This is not just about colonizing another planet, it's about building a better future for humanity. Let's begin with terraforming, a rather grand concept, isn't it? Essentially, it's the hypothetical process of modifying a planet's atmosphere, temperature, surface topography, and ecology to be similar to Earth's environment, making it habitable for humans and other life forms. Mars presents a significant challenge. Its atmosphere is incredibly thin, about the density of Earth's. This means minimal atmospheric pressure, making liquid water unstable on the surface. The atmosphere is also primarily carbon dioxide, about 96, with very little oxygen. And of course, it's cold. Really cold. Average temperatures hover around 62 degrees Celsius, 80 degrees Fahrenheit. So, how would we even begin? One proposal involves releasing greenhouse gases, things like carbon dioxide, methane, and even artificial fluorinated gases, into the atmosphere to trap heat and raise the temperature. This is akin to what's happening on Earth with climate change, but on Mars, it's an intentional act. However, simply releasing gases isn't enough. The Martian magnetic field is very weak, leaving the atmosphere vulnerable to being stripped away by the solar wind. We'd need to either create an artificial magnetosphere, a truly enormous undertaking, or find ways to replenish the atmosphere as it's lost. Another fascinating idea involves importing volatile compounds, water ice, ammonia, from asteroids or comets. This would provide both water and additional gases for the atmosphere. but the logistics of such an operation are substantial, to say the least. We're talking about redirecting space rocks, impacting them safely, and managing the resulting debris. Often, the first steps toward making Mars habitable won't involve transforming the entire planet, but creating localized, self-sustaining ecosystems. Think of enormous enclosed habitats, biodomes, that provide a controlled environment for humans and other life. These domes would need to be airtight, of course, and capable of regulating temperature, atmospheric pressure, and air composition. Inside, we'd need to create a closed-loop life support system, recycling air, water, and waste. This is where the concept of bioregenerative life support comes in. This involves using plants, algae, and other organisms to convert carbon dioxide into oxygen, purify water, and produce food. It's essentially creating a mini-Earth within the dome. The challenge is scaling this up to support a significant population. We'd need vast areas of agricultural land within the dome and efficient systems for managing resources. Another issue is radiation. Mars lacks a global magnetic field and a thick atmosphere, leaving the surface exposed to harmful cosmic radiation. Domes can offer some protection, but we might also need to bury habitats underground or use radiation shielding materials. Furthermore, long-term exposure to reduced gravity could have detrimental effects on human health. Artificial gravity systems, like rotating habitats, might be necessary, though these are incredibly complex and energy-intensive. Before we even think about large-scale terraforming, we need to understand and potentially modify the Martian soil, the regolith. It's not just inert dirt. It contains perchlorate salts that are toxic to humans and lacks the organic matter necessary to support plant life. One approach is to use genetically engineered microorganisms to break down the perchlorates, fix nitrogen from the atmosphere, and create a rudimentary soil structure. These organisms could also produce essential nutrients for plant growth. This process, known as bioremediation, could gradually transform the Martian regolith into something more hospitable. However, introducing terrestrial organisms to Mars carries risks. We need to ensure they don't disrupt any potential native Martian life if it exists, and that they remain contained within designated areas. Furthermore, we need to carefully consider the ethical implications of altering an alien environment. Another fascinating idea is to use 3D printing to create artificial soil structures, incorporating organic matter and nutrients. This could provide a stable growing medium for plants, even in areas with poor soil quality. It's important to remember that creating a sustainable ecosystem on Mars is not just about transforming the environment. It's about creating a balanced, self-regulating system that can support life for generations to come. That requires a holistic approach, considering all the interconnected factors: atmosphere, soil, water, energy, and biology. Now, let's consider the human element. Even if we could create a habitable environment on Mars, humans would still need to adapt to the new conditions. The lower gravity, the higher radiation levels, and the different atmospheric pressure would all pose challenges. Over time, natural selection would likely favor individuals with certain genetic traits that enhance their survival and reproduction on Mars. But what if we could accelerate that process? Genetic engineering offers the possibility of proactively modifying the human genome to enhance our adaptability to the Martian environment. This isn't about creating superhumans, but about mitigating the risks associated with living on another planet. For example, we could modify genes to increase radiation resistance, enhance bone density to compensate for the lower gravity, and improve the efficiency of oxygen uptake in the thinner atmosphere. This raises a lot of ethical questions, of course. Who decides which traits are desirable? What are the potential unintended consequences of altering the human genome? These are complex issues that require careful consideration and open discussion, but the potential benefits ensuring the long-term survival and well-being of humanity on Mars are significant. Beyond genetic engineering, we need to consider the broader process of evolution. Over many generations, natural selection would likely drive significant changes in the human population on Mars. We might see a decrease in height and body mass due to the lower gravity, an increase in lung capacity to compensate for the thinner atmosphere, and changes in skin pigmentation to protect against the higher levels of radiation. These changes wouldn't happen overnight, of course, but over centuries, they could result in a distinctly Martian human population. It's important to remember that evolution isn't a directed process. It's a random process driven by chance mutations and natural selection. We can't predict exactly how humans will evolve on Mars, but we can expect them to adapt to the new environment in ways that enhance their survival and reproduction. This raises the question of whether humans on Mars would eventually diverge enough from Earth humans to become a separate species. The answer depends on a variety of factors, including the degree of genetic isolation, the strength of natural selection, and the rate of genetic mutation. It's a fascinating thought experiment, and one that could have profound implications for the future of humanity. Genetic adaptation isn't limited to humans, of course. We'll also need to genetically modify plants and animals to thrive in the Martian environment. Plants will need to be resistant to radiation, drought, and extreme temperatures. They'll also need to be able to grow in the Martian soil, which is lacking in essential nutrients. Animals will need to be adapted to the lower gravity, the thinner atmosphere, and the different diet. This raises ethical questions about the welfare of animals in a Martian environment. We need to ensure that they are provided with adequate care and that their needs are met. But the potential benefits of genetically modified animals are significant. They could provide us with food, labor, and companionship. They could also help us to create a more sustainable ecosystem on Mars. And perhaps, in the distant future, we might even see the emergence of new, uniquely Martian species of plants and animals, a testament to the power of evolution and adaptation. Creating a flourishing, self-sustaining ecosystem on Mars will require a collaborative effort between humans, plants, and animals all working together to overcome the challenges of a new and unforgiving environment. For millennia, humanity has been confined to a single planet, a breathtakingly beautiful, yet ultimately fragile, home. We've always looked to the stars, but only now are we truly on the cusp of becoming an interplanetary species. This isn't simply about escaping Earth's problems, although that's a factor. It's about ensuring the long-term survival of our species and unlocking potential that remains dormant while we're limited to a single point of failure. Consider the history of life on Earth. Periods of mass extinction have repeatedly threatened its existence. A single catastrophic event, a large asteroid impact, a supervolcanic eruption, or even a self-inflicted crisis could wipe out all life as we know it. Becoming multiplanetary dramatically reduces that risk. It's a diversification strategy, like not putting all your eggs in one basket. But beyond survival, there's immense potential for growth. Establishing a permanent presence on Mars necessitates a level of innovation we haven't seen in generations. The challenges are enormous. Creating self-sustaining habitats, generating breathable air and potable water, producing food in a hostile environment, shielding ourselves from radiation, and developing new forms of energy. These aren't merely engineering problems. They demand breakthroughs in biology, chemistry, physics, materials science, and robotics. The solutions we develop for Mars will have profound implications for life on Earth. Imagine closed-loop life support systems that can purify air and water with unparalleled efficiency, or vertical farms that can produce abundant food in urban environments. These technologies aren't just for Mars. They can help us address some of the most pressing challenges facing our planet, such as climate change, resource scarcity, and food security. The economic benefits of becoming interplanetary are also significant. The development of new technologies and industries related to space exploration will create countless jobs and drive economic growth. The extraction of resources from Mars, such as water ice and rare earth minerals, could provide valuable materials for both Martian settlements and Earth-based industries. While the initial investment will be substantial, the long-term return on investment is potentially enormous. Think of the early days of exploration on Earth. The voyages of discovery led to the exchange of goods, ideas, and technologies that transformed the world. The colonization of Mars could be a similar catalyst for innovation and progress. It's an opportunity to create a new frontier for human ingenuity and enterprise. But it's not simply about profit. It's about expanding our horizons and pushing the boundaries of what's possible. Perhaps the most profound benefit of establishing a presence on Mars isn't economic or even practical. It's inspirational. Throughout history, humanity has been driven by a desire to explore, to discover, to push the boundaries of what's known. Space exploration embodies that spirit. The Apollo missions captivated the world and inspired a generation of scientists, engineers, and dreamers. But that spark has dimmed in recent decades. Establishing a permanent base on Mars could reignite that passion and inspire a new generation to pursue careers in STEM fields. It's a tangible goal, a concrete challenge that can capture the imagination of young people and motivate them to achieve great things. The challenges of Mars colonization are immense, and that's precisely what makes it so inspiring. It requires us to think outside the box, to develop innovative solutions to complex problems, and to collaborate across disciplines. It's a call to action for the best and brightest minds in the world. And it's not just about science and engineering. It's about art, literature, music, and philosophy. Creating a new society on Mars requires us to reimagine what it means to be human. What kind of culture do we want to build? What values do we want to prioritize? These are profound questions that deserve our attention. By setting ambitious goals like establishing a permanent base on Mars, we can inspire young people to pursue careers in STEM fields, fostering a new generation of scientists, engineers, and explorers. It's not just about preparing them for careers in space exploration. It's about equipping them with the skills and knowledge they need to solve the challenges facing our planet. The technologies and innovations developed for Mars colonization will have far-reaching applications in areas such as renewable energy, environmental sustainability, and healthcare. By investing in space exploration, we're investing in our future. We're creating a legacy of innovation and progress that will benefit generations to come. It's about fostering a sense of hope and possibility, reminding ourselves that anything is achievable if we set our minds to it. The colonization of Mars isn't simply about escaping Earth's problems. It's about creating a better future for humanity. It's an opportunity to build a society based on principles of sustainability, cooperation and innovation. We can learn from the mistakes of the past and create a more equitable and just society on Mars. Imagine a world where resources are managed responsibly, where energy is clean and renewable, and where everyone has access to education and healthcare. That's the vision we should strive for. It's not about replicating the problems of Earth on Mars. It's about creating a new beginning. A successful Martian colony will require a strong sense of community and cooperation. We need to create a society where everyone feels valued and respected, where differences are celebrated, and where everyone has a voice. This isn't just about building physical infrastructure, it's about building social infrastructure. It's about fostering a culture of trust, empathy, and mutual support. It's about creating a place where people can thrive, not just survive. We need to learn from the best examples of human societies and avoid the mistakes of the past. Ultimately, the colonization of Mars is about expanding our horizons and fulfilling our potential as a species. It's about pushing the boundaries of what's possible and exploring the universe in search of knowledge and understanding. It's about inspiring future generations to dream big and reach for the stars. It's a bold and ambitious undertaking, but it's one that's worthy of our time, effort, and resources. It's a testament to the power of human ingenuity, resilience, and determination. And it's a beacon of hope for the future of humanity. It's a vision of a brighter, more sustainable, and more hopeful future for all.